When Caterpillar unveiled a bulldozer so massive that engineers said it would flip over before it could work, one operator proved them all wrong by moving 3,000 cubic yards in a single shift, more than 5 smaller dozers combined. Before we continue with the video, if you're listening right now, help me prove something wrong. My wife said I wouldn't even reach 1,000 subscribers, but I believe stories about old machines like this deserve to be heard. Help me show her that these videos matter. Please subscribe to our channel and let's keep these old trains' legacies alive. May 1974, Peoria, Illinois. The specifications sitting on Chief Engineer Carl Bauer's desk seemed to violate every principle of stable machinery design his team had spent decades perfecting. Corporate management wanted a bulldozer with a blade 24 feet wide and operating weight exceeding 180,000 pounds, and enough drawbar pull to rip through bedrock that currently required explosives. The numbers made experienced engineers nervous. A machine this large would generate ground pressures that could cause it to sink in soft soil, require turning radii so wide it couldn't maneuver in confined spaces, and produce such massive torque that braking traction could flip the entire unit sideways. Design simulations showed the center of gravity dangerously high, with blade loads that could lever the rear of the machine completely off the ground during aggressive cutting. But mining companies were facing a crisis that conventional equipment couldn't solve. Open-pit copper mines in Arizona and coal operations in Wyoming were pushing deeper into overburden that measured hundreds of feet thick. Moving this material with existing D9 and D10 dozers required fleets of machines, armies of operators, and fuel consumption that was making marginal deposits economically impossible to develop. What the industry needed was a machine that could do the work of 5 dozers with a single operator, cutting costs while dramatically increasing the rate of overburden removal. The catch was that nobody had ever built a tracked dozer at this scale and made it controllable enough for precision work. Bauer's team started with the D9's proven drivetrain and began scaling everything up, not just in size, but in fundamental architecture. The power plant would be a turbocharged V12 diesel displacing 1,673 cubic inches, producing 700 horsepower at 1,800 RPM through a torque curve flat enough to maintain pulling power across a wide speed range. The transmission needed to handle torque multiplication that would generate over 200,000 pounds of drawbar pull in first gear, forces capable of snapping the track chains on smaller machines. The blade system represented the most radical engineering challenge. 24 feet of curved steel weighing 11,000 pounds would be lifted by 4 massive hydraulic cylinders operating at 5,000 psi, controlled through a pilot hydraulic system sensitive enough for finish grading yet powerful enough to punch through frozen ground. Nobody had attempted hydraulic implement control at this scale, and the risk of catastrophic failure seemed to outweigh potential benefits. By November 1974, the first prototype, D11, was taking shape in Caterpillar's East Peoria facility, a machine so large that the assembly building's overhead cranes required reinforcement just to move major components. Would this engineering gamble create the future of earth-moving or the most expensive failure in Caterpillar's history? The challenge that kept Bauer awake at night wasn't raw power. Caterpillar's engineers knew how to build strong drivetrains. The real problem was making a 180,000-pound machine respond like the smaller dozers operators had spent careers mastering. Every input had to be amplified correctly. Too sensitive, and the blade would oscillate wildly. Too sluggish, and operators couldn't achieve the precision that separated skilled earth-moving from expensive mistakes. Hydraulic engineer Janet Morrison led the team developing the pilot control system, a network of miniature valves and pressure sensors that translated tiny joystick movements into massive hydraulic flows. The concept was elegant. Operators would move small hand controls that sent low-pressure hydraulic signals to main control valves, which then directed high-pressure oil to the blade cylinders. This gave operators the mechanical advantage needed to control tremendous forces with fingertip pressure. But scaling the system to D11 proportions introduced problems that had never been solved in production machinery. The main control valves needed to handle oil flows exceeding 200 gallons per minute while responding to pilot signals measured in fractions of a second. Any delay between operator input and blade response would make the machine feel sluggish and unpredictable, exactly what critics feared from a dozer this size. Morrison's solution involved designing spool valves with tolerances measured in 10,000ths of an inch, precision normally reserved for aerospace applications. The valve bodies were machined from solid steel billets and fitted with hardened spools that could withstand the constant hammering of high-pressure oil flow. Each valve underwent pressure testing that simulated years of operation, searching for any weakness that might cause failure in the field. The hydraulic pump presented equally daunting challenges. Supplying 200 gallons per minute at 5,000 psi required a pump driven directly from the engine's power takeoff, consuming over 140 horsepower just to pressurize the hydraulic system. Heat generation was tremendous, necessitating oil coolers the size of automobile radiators and filtration systems that could remove contaminants smaller than talcum powder. Testing began in January 1975 with controlled blade movements in the factory yard. Engineers watched nervously as the first operator lifted the massive blade through its full range of travel, looking for any sign of instability or loss of control. The blade rose smoothly, responding to gentle pressure on the joystick with movements that seemed impossibly precise for something weighing as much as a loaded dump truck. Then they tried cutting actual dirt. The blade bit into packed clay with force that sent shudders through the entire machine frame. The rear tracks lifted slightly as blade load transferred weight forward, exactly the levering effect that critics had warned would make the D11 uncontrollable. The moment of truth had arrived. March 1975, Arizona Desert Proving Grounds. The first production, D11, serial number 001, sat motionless in caliche hardpan while Chief Test Operator Ray Hoskins studied the problem developing in front of him. After 40 hours of evaluation work, a hydraulic leak was weeping fluid from the left blade lift cylinder, creating a slowly expanding dark stain on the pale desert soil. The failure was exactly what skeptics had predicted. At 5,000 psi system pressure, even microscopic imperfections in cylinder seals could grow into catastrophic failures that would dump the blade without warning. Hoskins had been operating heavy equipment for 23 years and understood that hydraulic systems this powerful had no margin for error. A sudden pressure loss while carrying a full blade of material could drop 30,000 pounds of rock onto the machine's frame, or worse, cause the entire dozer to pitch forward unpredictably. Back in Peoria, Morrison's team tore down the failed cylinder and found the source of the leak. A seal groove machine slightly out of specification, allowing the backup ring to extrude under pressure. The tolerance error was less than 5,000ths of an inch. Invisible to the naked eye, but catastrophic at operating pressures. Manufacturing standards would need to improve dramatically. The second failure emerged during ripping trials in Wyoming coal country. The D11's rear-mounted ripper, a massive single-shank assembly designed to fracture bedrock, generated forces that twisted the mainframe in ways smaller dozers never experienced. After 60 hours of heavy ripping, metal fatigue cracks appeared in the frame castings where ripper loads transferred to the main structure. Structural engineer Thomas Chen examined the fracture patterns with growing concern. The cracks followed stress lines his computer models had predicted, but they were appearing far sooner than calculations suggested. Either the models were wrong about load distribution, or operators were subjecting the machine to impacts that exceeded design assumptions. Probably both. The modifications required to address these failures were extensive. Cylinder manufacturing moved to a dedicated facility with climate-controlled machining centers capable of holding tolerances within 0.002 of an inch. Frame castings were redesigned with additional ribbing and material thickness in high-stress areas, adding 8,000 pounds to the machine's already massive weight. The ripper mounting system was completely re-engineered with shock-absorbing elements that cushioned peak loads. Each fix revealed new problems. Stronger frames transferred more vibration to the operator platform, requiring isolation mounts that added complexity. Heavier cylinders needed larger pivot pins, which meant redesigning the blade mounting points. The domino effect of engineering changes threatened to delay production by months, while mining companies waited impatiently for a machine that was still breaking in fundamental ways. But Hoskins had noticed something during those early trials that nobody else was talking about yet. Ray Hoskins had been running the problematic D11 prototype long enough to recognize something the engineers weren't seeing from their test data. Despite the failures and setbacks, when this machine worked properly, it moved earth with an efficiency that defied conventional wisdom about dozer productivity. During a particularly productive afternoon in the Arizona Caliche, Hoskins had pushed a continuous cut 400 feet long, carrying a full blade of material that smaller dozers couldn't even lift. The key was understanding how blade load affected the machine's balance. Rather than fight the forward weight transfer, Hoskins learned to use it, adding down pressure to the cutting edge that helped the blade penetrate hard material. The technique required completely relearning operator instincts developed over decades on smaller equipment. Traditional dozer work involved frequent blade adjustments, constantly fine-tuning the cutting angle and depth to maintain optimal load. But the D11's massive blade momentum meant that every adjustment took longer to execute and had more dramatic effects on machine stability. Hoskins discovered that the secret was anticipation. By reading the ground conditions ahead and making control inputs early, he could keep the blade loaded continuously without the jerky corrections that plagued less experienced operators. The pilot hydraulic controls, which skeptics claimed would be too sensitive for a machine this size, actually provided the precise response needed for this smoothed operating style. The breakthrough came during a demonstration for Phelps Dodge Mining Company executives who were considering ordering the first production D11S. The mine superintendent challenged Hoskins to move a marked volume of copper over burden in a single shift, setting a target based on their current fleet of 5 D9s operating the same material. Hoskins spent the first hour studying the cut, planning his approach, and selecting blade angles that would maximize load carrying while minimizing track slip. Then he began the steady rhythm of cutting, carrying, and spreading material with the methodical precision of a machine that wasn't just moving dirt, but proving a concept. By shift end, survey crews measured the results. 3,200 cubic yards moved, precisely placed, and finish graded to within 6 inches of final elevation. The 5 D9s working the same material typically moved 2,800 yards combined, with rougher finish work that required additional cleanup passes. 1 D11, 1 operator, 1 fuel supply, dramatically outperforming the conventional approach. The Phelps Dodge engineers began calculating the economics. Fewer operators meant lower labor costs. Single machine operations simplified logistics and reduced maintenance overhead. Most importantly, the D11 could work bench heights that required multiple passes with smaller equipment, fundamentally changing how they could design their mining operations. The orders started arriving before the machine even returned to Peoria for post-demonstration inspection. By late 1976, Caterpillar's assembly facility was producing D11s at the rate of 2 machines per week, each one incorporating lessons learned from field failures and operator feedback. The manufacturing challenges of building dozers at this scale had required completely rethinking assembly line processes designed for smaller equipment. The undercarriage system became the benchmark for heavy-duty track design that would influence crawler tractor engineering for decades. Each track link weighed 285 pounds and was designed with grease-lubricated pins that required service every 250 operating hours. The track frame supported 7 bottom rollers per side, each one a precision assembly weighing 600 pounds and riding on sealed tapered roller bearings designed for mining truck applications. Quality engineer David Park implemented statistical process controls that tracked every critical dimension across the manufacturing sequence. Pin bore tolerances, bushing wall thickness, even the hardness of individual track shoes were measured and recorded, creating a database that allowed Caterpillar to identify manufacturing trends before they became field failures. The hydraulic systems received similar attention after early seal failures threatened to derail production ramps. Every cylinder was pressure tested to 7,500 psi, 50% above normal operating pressure, and held for 4 hours, while technicians examined every seal surface with magnification. Valves were flow tested and calibrated individually, with response times recorded for each unit to ensure consistent performance across the production run. But the most significant evolution was happening in the engine room, where Caterpillar's diesel engineers were pushing the 3412 power plant beyond its original design limits. Early production D11S made 700 horsepower, but mining customers wanted more. Turbocharger upgrades, improved fuel injection timing, and enhanced cooling systems gradually increased output to 770 horsepower without sacrificing the reliability that underground mining operations demanded. The transmission received corresponding upgrades to handle increased torque. The original 3-speed powershift design proved inadequate for the load variations encountered in production mining, particularly when machines transitioned from cutting to carrying operations. A 4-speed design with improved clutch packs and upgraded planetary gear sets provided better speed matching and reduced the torque converter slip that was consuming fuel and generating heat. Field modifications became standard production features as operators discovered ways to improve performance. Extended handrails for better access to service points, relocated hydraulic ports for easier hose connections, even repositioned toolboxes based on which tools mechanics needed most frequently. Each change reflected real-world experience being incorporated into production design. By 1978, the D11 had evolved from controversial prototype to proven production machine, with over 200 units operating worldwide. But the real test was still ahead, in applications that would push the design to absolute limits and reveal whether this oversized dozer could truly outperform conventional equipment fleets. The Morenci copper mine in southeastern Arizona became the ultimate testing ground for whether engineering ambition could overcome practical skepticism. Phelps Dodge had committed to a massive expansion of their open-pit operations, requiring removal of 400 million tons of overburden to expose copper ore bodies lying beneath 600 feet of waste rock and desert hardpan. Mine operations manager Frank Delgado faced a decision that would define the project economics. Traditional approach called for a fleet of 20 D9 dozers working in coordinated teams requiring 20 operators, extensive maintenance facilities, and fuel consumption exceeding 50,000 gallons per month. The alternative was betting on 8D11 to do the same work with a fraction of the labor and logistical overhead. The financial arithmetic was compelling, but risky. Each D11 cost $485,000 compared to $198,000 for a D9. If the big machines failed to deliver their promised productivity or suffered reliability problems that kept them down for extended repairs, Phelps Dodge would have invested over $3.8 million in equipment that underperformed cheaper alternatives. Delgado ordered 4 D11s for initial evaluation, with options for 4 more if performance met projections. The machines arrived in September 1977 and were immediately put to work on the most demanding application imaginable, pushing 800-foot cuts through material ranging from loose, decomposed granite to cemented caliche that resisted even aggressive ripping. Operator Carlos Mendoza drew the first shift on D11 number 347, a machine fresh from Peoria with just 40 hours of break-in time. The cut ahead of him was 780 feet of downhill grade through material that had been ripped the previous shift, creating a loosened but still challenging push for any dozer. Mendoza throttled up, dropped the blade, and felt the machine settle into the characteristic working posture that D11 operators learned to recognize. Front end loaded, rear tracks digging for traction, the big diesel pulling smoothly at 1,650 RPM. The productivity numbers that emerged from those first months transformed mining industry assumptions about optimal equipment sizing. Mendoza and 3 other D11 operators consistently moved more material per shift than their counterparts running 5 dozer teams on adjacent benches. Fuel consumption per cubic yard moved favored the D11S by 18%, reflecting the thermodynamic efficiency of running 1 large engine versus 5 smaller ones. Maintenance costs proved surprisingly favorable despite initial concerns about complexity. The sophisticated hydraulic systems required more frequent service than mechanical controls, but the reduced fleet size meant fewer machines to maintain overall. Track life exceeded projections, with the first major undercarriage renewals not required until 5,800 operating hours, well beyond what smaller dozers achieved in similar applications. Delgado ordered the remaining 4 D11s 6 months ahead of schedule. By 1985, over 800 D11s were operating worldwide, fundamentally changing how mining and heavy construction companies approached large-scale earth-moving. The machine that engineers had called too big to control had become the standard for applications where moving maximum material with minimum operators determined project economics. The ripple effects extended far beyond Caterpillar's product line. Competing manufacturers rushed to develop their own ultra-large dozers, creating a category of equipment that hadn't existed before the D11 proved the concept viable. Komatsu introduced the D475, Dresser launched the TD40, and even smaller manufacturers attempted to capture market share in applications where only the biggest machines made economic sense. But the D11's real legacy was proving that sophisticated control systems could be scaled to handle forces that would have seemed unmanageable just a decade earlier. The pilot hydraulic technology that skeptics dismissed as too fragile for mining applications became industry standard, eventually appearing on dozers of all sizes. The lessons learned about frame design, undercarriage loading, and hydraulic system architecture influenced every subsequent generation of crawler tractors. The engineering team that created the D11 had solved a problem that extended beyond simple machine design. They proved that human operators could effectively control equipment operating at scales that exceeded direct physical capability as long as the control systems provided appropriate feedback and response. This principle would later enable everything from modern excavators to autonomous mining trucks, technology built on the foundation that the D11 established. Yet the story also revealed uncomfortable truths about the direction of earth-moving equipment development. As machines grew larger and more sophisticated, the number of operators who could run them effectively diminished. The D11 required skills that took years to develop, an understanding of machine dynamics that couldn't be taught from manuals alone. The industry was creating equipment that outpaced the available workforce's ability to utilize it fully. Modern D11s now produce over 850 horsepower through electronically controlled diesels, move earth through GPS-guided blade systems that maintain grade automatically, and incorporate emissions controls that would have seemed like science fiction to the engineers who built that first prototype. The machine has evolved continuously for nearly 5 decades, each generation adding capability while maintaining the fundamental architecture that made the original design successful. The Morenci mine still operates D11s on the same benches where Carlos Mendoza proved that one big machine could outwork 5 smaller ones. The faces have changed, the technology has advanced, but the principle remains. Sometimes, the solution everyone calls impossible is simply waiting for someone brave enough to prove it works. But here's what nobody talks about. If one operator on a single D11 could outperform 5 operators on 5 smaller dozers, why did the industry eventually develop autonomous mining trucks instead of autonomous dozers? And what does that reveal about the true limitations of even the most controllable machines?